So we're talking about optimizing beer production with Sorba. As I said there before, my name is Peter Horsburgh. I'm the Australian Pacific Managing Director of SORBA.ai. I'm also the author of The 5 Habits of an Extraordinary Reliability Engineer, and you may hear either Ellie or May in the background. If they need to interrupt me, call me out and say, "Hey, Seven," that is my nickname. So if you good people now can say that you've spent some time with Seven. Other than writing books, I fly aeroplanes. I've had a pilot's license here in Australia since I was about the age of 16. Being a mechanical engineer, and I love cars as well. And on the right-hand side, just over here, is the my latest project, which is actually going to appear in this webinar today. Is the Mazda RX-8. So my sons and I have a little bit of habit. Well, we love cars. We're a car family, and this is my project. Is sorting out this Mazda RX-8, and I'll talk about that a little bit later. So if you hang to the end there, everyone, there is some prizes to be had. All of you are going to get access to the Sorba University. All of you are going to get access to a Sorba Smart Data Engine virtual machine, i.e. you will have the ability to learn Sorba through the university and the virtual machine. But only one of you will get a complimentary proof of concept, i.e. you spend time with the team, and we will analyze some data such as what you're going to see here today through Sorba. So that's a guided data analysis through Sorba. Will help through that proof of concept, as we call it. And one only will get a signed copy of the book. To get your signed copy of the book, you must be here at the end of the webinar. So without further ado, everyone, let's get into what we are going to talk about today, the agenda. First thing I'm going to talk about is how to make beer. The second thing that I'm going to talk about is I'm going to talk about how machine learning works in the context of optimizing processes, and the key process here today is beer making. Okay, I do happen to like a drink of beer. I follow the pilot's rule, i.e. I only drink alcohol or beer on Friday and Saturdays. Okay, otherwise during the week, I don't drink beer. So we've got some examples here to work through as well, where we're talking about beer and also related processes around beer making. Okay, awesome. How to make beer. Here's a basic introduction in how to make beer, just for the context of what we're talking about here today. I'm not going to turn you into an expert on making beer, okay? But the basic beer making process, and I'll just grab my pen here, everyone, is the first part of it is malting, okay? So barley is soaked in water, it's allowed to germinate and then dried in a kiln, okay? This process converts the starches in the barley into fermentable sugars, okay? And fermentation is all about making the alcohol that is contained in the beer, okay? The next one is we mash it. The malted barley is crushed and mixed with hot water and in a vessel called a mash tun, okay? This step activates the enzymes that break down the malt's starches into sugar, creating a sweet liquid known as wort. From there, the wort is transferred into a kettle and boiled. Hops are added. I'm not a big fan of a lot of hops in my beer because it tends to make it fruity, okay? So they're added during the boil to add in bitterness, flavour and aroma to the beer. And obviously there's a whole heap of different recipes in here around the different types of beers. You know, I like black beer or dark beers, not the clear beers. That's my personal preference, and I'm sure that there's lots of other different people around there love their beers in different ways. After the boiling process, we then cool it, okay, so that it's at a temperature suitable for fermentation, and that fermentation temperature is roughly, and I'm, here in Australia we talk metric, 20 to 22 degrees or 68 to 72 degrees Fahrenheit in the imperial scale. Okay. Fermentation, the cooled wort is transferred to a fermentation vessel and the yeast is added. Okay. The yeast is the magic stuff. It consumes the sugars in the wort, producing alcohol and carbon dioxide as byproducts. Okay. The carbon dioxide is the bubbles in the beer. Okay. And fermentation can take anywhere from a few days to several weeks, depending upon what type of beer you are actually making. Okay. So there's the basic process. After the fermentation is complete, the beer is often conditioned to allow the flavors to mature and mellow. This can take place in a fermentation vessel or in separate tanks. So we can transfer the beer into separate vessels. Once the conditioning is complete, I'm up to stage 7 here, we then package and then maturation. So maturation, if we're talking about bottles of beer, they'll leave it in the bottles of beer either at room temperature or in cold storage to allow the flavors to develop even further before consumption. When you're making beer, it's very, very important that you monitor temperature, pH, as in acidity levels, and your yeast health to ensure the quality and consistency of the final products. Okay, so there's the basic overview. I'm not turning you into experts on how to make beer. So then what we want to do is move into the beer making challenges. Number 1, the biggest challenge around making beer is, as so I'm informed, is quality control. Maintaining the consistent taste, aroma, and quality across batches is absolutely crucial. Okay. It can be challenging at times due to the variations in ingredients, equipment, and environmental factors. Summer, winter, obviously, to ferment beer, we have to keep it at 22 degrees and we have to make sure, or thereabouts, and make sure that it stays there no matter the season. Like everyone, I don't know anyone that doesn't want to be efficient. We want to maximize production efficiency whilst minimizing costs, i.e., get the most out of something costing you the least. Okay, so energy in Australia is becoming more expensive, as well as labor, and obviously raw materials has an effect as well, going up there as well. Supply chain management, and you'll notice that I've circled some in red to you today because we want to talk about those in particular today. Supply chain management, okay, making sure that you have got your hops and malt, and that could be challenging due to availability, pricing, and quality. They may have had a bad season, a bad growing season, say for example in hops, and hops are hard to get, so you have to actually make sure that you've got enough hops to make sure that you can actually brew the beer. Equipment maintenance. As you saw in the process relies upon things working over a period of time to make sure that you do not throw away any batches of beer because they're not going to meet your quality spec. Regulatory compliance, okay, you need to maintain your standards related to brewing. It is a foodstuff for consumption. Okay. Labeling, packaging, and distribution. Okay, you've got to make sure that everything is in check from a regulation point of view during all of those processes. Didn't say it was easy to make beer. Inventory management. Okay, you've got to keep up with your raw materials, your work in progress, and finished goods to meet demand without overstocking or running out. There's a big problem if you run out of beer for some people. Okay, the demand for beer is quite large here in Australia. It's a popular product, and people do get very disappointed if they cannot get their favourite brand of beer. Market demand fluctuations. You've got to anticipate it. Obviously, we're dealing with a food product here, and we don't want to waste anything. Sustainability. Everyone is trying to be more sustainable. We use water in the process for making beer. We use energy. There is a number of waste products that we have to use. Okay, and obviously we're using packaging materials, so we need those environmental and cost saving there as best as we can. Technology integration. That is us. That's why it's green. Adopting and integrating new advanced brewing technologies, and I very much hope today to give you some insight into what people are doing around the world. Okay, like everywhere, competition. We want to stay ahead of our competitors and basically do well, right? And do well in a crowded market. There is a number of different craft brewers starting to appear, especially here in Australia. That is providing competition for all of the others, especially the big brands. All right, let's move on there, people. When we talk about SORBA, okay, there is a number of typical needs that people come and talk to us about. Okay. At the end there, you will see there's a big red arrow, and I'll get to the big red arrow in a second. But need number one, is data sent to a remote team. Need number two is the need to remove live work. What does that mean? The need to put people at risk working on live equipment. People come and talk to us about that, on how we can do that. Need number three is data to carry out automated maintenance tasks. So instead of getting people to actually measure stuff that they need to do to maintain the equipment, SORBA can collect that. Need number four, live and condition monitoring in one place. Okay, so everything comes into one place. Our IT friends call this a unified namespace. Need number five, to relieve staff of data analysis tasks. There is a big move these days. You know, ChatGPT is the thing that I'm talking about here. It doesn't fulfill all of the needs of the workforce. It can automate a number of things. It can do lots of things, but it's still the human that needs to make decisions. It cannot remove the humans out of it. If we can remove that need for the human to not value add by doing data analysis, i.e. we get the computer to do it, okay, and the humans can actually do what humans do best, is make decisions on the best way to go and be creative. Okay, so people come and talk to us about that. How can we relieve staff of data analysis tasks? Need number six is early warning of faults. Me being a reliability engineer, this is my forte. I love this. This is my bread and butter. I so wish that I had SORBA in my corporate life and make life so much easier. But today, what we are talking about today, everyone, is need number seven, to optimize something such as energy consumption. And what we mean by optimize something is minimizing or make best use of said thing, whatever said thing is. It can be energy, it can be any other sort of inputs into a process. That's what we're talking about today, and we're going to talk about it in respect to beer. We've got some examples around that. Okay, so as a bit of a primer to get you in the mood of down the path of how this actually works, is we ran a webinar earlier on machine learning for fault finders. And in this webinar, just a quick recap, I hope you were there. We love doing webinars to educate people. We introduced this little green guy. He's called a SORBot, and he reads tags. And what you can do is teach him what is normal, okay? And he can actually let you know what is normal and what is abnormal, okay? So you teach him what is normal. You teach him as the human. This is where the humans come in. The humans teach the SORBots what is normal and what is abnormal. And then they do their thing. And they do things something like this. So our little SORBot is really, really good at recognizing difference in behavior. I'm going to say that again because it's really, really important when it comes to optimizing a process that we lever off that ability for the SORBots to recognize different behaviors. And we can use that to our advantage in optimizing. In this case here, he's got a sine wave and he's recognizing the little red blips on the sine wave. And this is how he does it. He says the rest of the sine wave is normal, but these little red blips are actually abnormal. And he'll tell us where that is, which is awesome because we can lever off that. Now, I mentioned there earlier about my little red car, the Mazda RX-8. It is a rotary engined vehicle, and I found this on Wikipedia as the best way to explain how a rotary engine works. And we have actually pulled this engine apart. That was part of what the work that we did to learn about this car. And we rebuilt the engine, and here is the car, the photograph just here on your right. Here is the car on the dyno tuner. Why did we put it onto the dyno tuner? We wanted to maximize the power coming from our engine and minimize the fuel consumption. So in automobile space, what we have to do is put that onto a dyno tuner. In this case, we can guess, but it's far better to actually measure the power output from the car so that we can actually maximize that and tune it so that we get the most power, okay, using the least amount of fuel. So our inputs into our rotary engine is fuel. It sucks air in as part of the process, but fuel is the one that we are really, really interested in. And we want to maximize the power coming out of the rotary engine. For those that don't know engines, there is a correct air fuel ratio that is required to be burnt to actually achieve the maximum power or minimum fuel economy. Okay. Now I've put here there's a green zone and there's a green zone. Right, the right thing, Seven. There's a green zone and 2 red zones. So a lean mixture means that we are not putting enough fuel into the air, which means we get poor power out because we're not putting the energy in. If we have the correct fuel ratio, we'll get good power out of the engine. If we put too much fuel in, i.e. they call that a rich mixture, we're putting too much in, we've got the fuel and air rich with fuel, we'll see poor fuel economy. If we go too far, there is extremes with this. If we lean the engine out too far, the engine won't run because we're not putting enough energy in it. And likewise, if we put too much a rich mixture in there, the engine won't run. Because there's too much fuel for the air to actually burn. Now that's a simplistic way of seeing it, but that the takeaway of this is if we get the correct air fuel ratio right, we are maximizing our fuel economy, and our power. Now, truth be told, at low power settings, we want it leaner. At higher power settings, we want it richer. This is some of the stuff that I learned by putting the car on the dyno tuner and actually seeing some data. All right, so we can then, coming back to our SORBot, okay, I'm building up here. So if I introduce our SORBot and our possible operational envelope for our car, and here is all the possible areas that we could operate our car, just selected randomly. That's what represented by these dots in here, that we can successfully operate our car, and we'll achieve an outcome. Okay, so he can look at this data and, depending upon the goals, recommend I'll start that again. He can recommend where to set the mixture depending upon what we tell him we want. Okay, so in the car, if I wanted to minimize my fuel economy, for example, my SORBot would recommend a lean mixture, okay, to achieve that fuel economy. However, if I wanted more power, he would recommend a richer running, or adding more fuel to the fuel to achieve that goal. So depending upon our goals, our SORBots can recognize the difference in behavior and optimize the operation of the system to achieve that outcome. This is how they do it. They're using that key skill that machine learning has, recognizing difference in behavior, looking at the outcome that you want, and learning from that to say, hey, at this particular point here, I need to operate the mixture here to achieve the power, okay, to achieve maximum power, because this is where I have learnt from my operations where I'll actually achieve maximum power, even though I could operate it at these different levels here. Okay, this one didn't work before, it doesn't achieve the most power. This one doesn't achieve the most power, okay, and this one doesn't achieve the most power, but this one does. So he will learn that by viewing the operation of the plant over time. He recognizes difference in behavior. The beauty of things in industrial plant over motor cars is that we can generally get that power data from somewhere. It's a little bit harder in the RX-8 because it doesn't know what power it's making at the rear wheels. Hence why we put it on the dyno tuner to figure that out, so we can get this to do this optimization. So now that we've got a bit of a feel for how our little friendly SORBot works here, here is some examples of where they've applied it to beer. Now, I've put this photo up here there, ladies and gentlemen, because this is a process where, as you can guess by the red smiley faces, where the SORBot was not making the beer, controlling the process, and you'll see there is some contaminants here, and here is where the SORBot was making the beer. They actually ran an experiment with and without the SORBot, and there is the visible differences in the beer product. Now, also, the interesting thing is if you notice up here and notice on this one, for our beer making connoisseurs, this one's actually got a little bit of a head and this one isn't. So we've got customers around the world actually using the SORBots to optimize their beer production, in this case here, making a better quality beer. Okay, there's a visible difference that you can see. Now, here is an example of where we've let the SORBot loose on a filter. He is controlling this filter process where the beer comes in and the beer comes out here, filtered. Okay, and there's some ingredients that go in here. There's water that goes in there as well. And we've got some filter leaves, and cut a long story short, in this one factory making one particular brand of beer, the outcome was that they got 30.6% more beer, right, for the products added, with a 42.6% lower turbidity. And that's just letting the SORBot learn and optimize the process over what a human would do. I've got some more examples here, people. Sorry, before I go to the more examples, this is what it looks like inside SORBA. I thought I'd put this slide here just to show you how much data this little guy is analyzing and figuring out where the optimal point is. Okay, this is a bit of a screenshot inside SORBA. As you can see, there's lots of stuff going on there. Okay, and we call it advanced process control. It's the module that we actually call it. As you can see, it's doing a lot of data work at that one time. You know, if you'd like to try this on your process, please give us a hoy. We can handle, it can handle, or the SORBots can handle lots of data at once, as you can see here on the screen. And the blue and the red line basically represents the gap or the area for improvement based upon the data that's presented. Okay, or another way to put it is the gap, the process that can, the amount of process improvement that can be gained by from what the SORBot has learnt, or where the best place is to operate this process. Same process, different beer. Same process, different beer. We told our little friend here to maximize the beer filtered. Okay, same process, different beer. And lo and behold, he got more beer and less and better turbidity, but he didn't achieve the dramatic result as brand one. So he has relearnt this new brand and it's got a different outcome. Okay, the results are a little less dramatic, but what we're trying to show you here is that if you swap the different products, he can also handle that too. However, the result is not as dramatic. In this case, he has figured out that he can achieve 14.8% more beer rather than the rather large number last time. So he will actually modify based upon the data that is presented. Okay, he will learn where the best set points is, even though things change. I thought I'd put this slide up and show you a visible difference. And we've seen some of the outcomes, but a visible difference in the data between when SORBA is controlling things versus a human. So humans are really good at variation in this way. Like, we can handle change and variation, okay, and creative and all that sort of stuff. It does have its downsides. As you can see here, you can see the difference between how SORBA controls the process versus the human. Now, that's great. What's the outcome? If you have a look at the outcome down here, earth dosage is a material that is used, or a product that is used in filtering beer. Okay, so for 8,000 liters or 8,000 hectoliters of beer, the earth dosage was 1,200 liters with SORBA. Okay, so this is the result of this process up here. Without SORBA, i.e. the human achieved the same result, 8,000 liters of beer, sorry, 8,000 hectoliters of beer filtered, but they used 1,700 liters. Okay, so that's a 500 liter difference in, into an input into your process. All right, so I put this slide up here just to show how consistent our little SORBA friends, the SORBots, are at actually operating a process compared to what a human would do. Okay, so just to give you some examples there. Now, who's using SORBA? Here's some companies here that are using SORBA around the world. Okay, and those in the food and beverage industry would recognize one very big brand there on that screen. So these people are using SORBA in different ways. Some are using it for data collection, some are using it for fault finding, some are using it for advanced process control or optimization, as we call it, and some are using it all of the above. Okay, so where can this technology be applied? This technology can be applied to refrigeration, boilers and heaters, dehydrators, kilns and furnaces, filters, membranes and heat exchangers. We've seen a little bit of that already. Fans, compressors, turbines, engines, transport systems, building management systems, you name it. If you need to optimize a process, okay, we are willing to have a look at that and guide you through the process. So we don't like to do it for you. You are the best people to use the tools to optimize your process. We are here to supply you the tools and the education on how to do it. We've always said the subject matter expert, i.e. the engineers or the process people that are controlling the process, are the best to actually teach the SORBots rather than us. So let's talk about some examples. Refrigeration. So remember in the example earlier, we've got to cool the beer, the process of cooling the beer. So that's why I included here. So what we do there, just to give you an idea, is we have a little bit of what we call a plant discovery, i.e. we understand how the plant is configured. In this case with refrigeration, we like to have a look at some of the thermodynamic diagrams, so that we have an appreciation of the performance of where the plant could be. We then analyze some data offline to actually create the SORBot. And the SORBot is the little guy that actually controls the process. Now, before I go too far, some people are not comfortable with the SORBots actually controlling the process directly. That is fine. We can get the SORBots to advise what is the best set point, and the human decides whether that's right or wrong based upon what the human is experiencing at that point in time. That is fine too. We've got people in between. So we've got people actually letting the SORBot actually control the process, as you've seen there earlier today, and we've got people using him as an advice. So basically, we had to do some offline data analysis to find the gap in performance, okay? To find the gap in performance using your data. In this case here, the optimal line is the green line. Then what we can do in the vein of what I've just spoken about is that the SORBots actually do their calculations live, i.e. they give you feedback what's happening here and now. Normally they update their calculations for every 5 seconds. They actually work themselves every second. So we can actually build a little operations dashboard so you can actually watch what's going on. Okay, and on this refrigeration plant, we're seeing somewhere around 5 to 10% in energy savings by optimizing suction and or discharge pressure. We've got customers already seeing that right now. You can actually see that on the dashboard. We can actually do those sort of calculations for you live. Okay. Boilers. So in the beer making process, we've not only got to cool the stuff, we've also got to heat the stuff. We've got to boil the raw products to make beer. So we can do the same thing with a boiler. We can take the data from the plant offline. In this case here, we're looking at gas and steam flow. So the boiler is gas powered versus steam flow, and we can basically start to teach and get the bots to learn and recognize where the optimal behavior is. And in true SORBA style, we can create an operations dashboard where you can actually view the status of the plant, a little picture of the plant, and what's actually happening and what the SORBot is forecasting that you need to know. So we have found that the SORBots in boilers are consistently generating 5+% in fuel savings with no capital investment to the plant. i.e., we do not change the plant whatsoever. It's just controlling it better using the machine learning. Okay, awesome. Now, last one here, ladies and gents, is the biomass boiler for kilning. Again, I picked this one because it's sort of related to beer production, because you've got to actually control the temperature in your beer. Error in this case here is less than 3%, which represents a 50% improvement over temperature control. Okay, so with beer making, okay, this biomass boiler may be a little bit extreme for the beer making, but you can get the idea here that we can use the SORBots also to improve the control of temperature. Thank you for attending today. Here is my contact details. Please feel free to email me at peter@sorba.ai. If you haven't found me on LinkedIn or Sorba on LinkedIn, this is where we are. You'll also get some login details to the university at for Sorba, where you can learn more about the platform, how to do things, and more examples of different things that you can actually do with Sorba. So we're all about tools and process and teaching you how to optimize your processes. If you want to learn more at any point in time, there's a quick QR code to book in and or to scan and book in with myself to your particular needs. So without a further ado, everyone, thank you very much for attending today. Hope you enjoyed the webinar and look forward to catching up in the very near future. Thank you, everyone.